Yes, welcome back. So in the previous video, we've been discussing about an analysis of an 4-bar mechanism. So in this video, we're going to be discussing about an slider crank mechanism. Yes, coming to the slider crank mechanism. So in a slider crank mechanism, an absolute velocity is a velocity of a point measured from a fixed point. See here we're going to find out, or we're going to identify the uh, velocity of a point from where it is the point has been fixed. Normally the ground or anything rigidly attached to the ground, it will be not moving. That is what we call as a fixed point. So relative velocity is the velocity of a point measured to a relative to the another that it might be, that is itself will be moving. So considering a link AB and a pin at an A, where we can able to see this. Considering a link AB, where it is a moving a pin with at AB, and the velocity angular velocity, where you can able to see this point at AB, where you going to be one is fixed and one will be the moving. So considering a link AB pinned at A and a revolving about A at an angular velocity m. So point B moves in a circle relative to point A, but its velocity is always velocity will be always tangential and ends at a 90° to the link. A convenient method of denoting this tangential velocity is Vb. That is the meaning of velocity of B with respect to the relative velocity to A. This method is not always suitable. Normally it is not suitable, but in some conditions we are going to use this method in order to find the absolute velocity of a slider crank mechanism. Now we can able to see this, the point A is fixed, which is rotating at an angular velocity, and the velocity at the point B with respect to A. Considering a sliding link C, that it can able to slide the link on from A to B. We can able to see that link can able to slide A to B. The direction can only be the radial relative to the point as shown in the figure. So the direction will be only the relative to the point as shown in the figure. If the link AB rotates about A, this link AB rotates about this A, that is about this point A. At the same time, the link C will be having a radial and tangential velocity. Here the link C is not there. Means if you go to connect the link C or the one more link, what happens? So now the link AB will be rotating at about A. At the same time, even the link C will be having a radial and a tangential velocities. So this is now we can able to see for the same slider crank mechanism. So the link C is been attached. Now the link C will be having a tangential motion. We can able to see this is VC, which will be moving in a tangential motion, and this is the A is nothing which having in a radial motion. See, when A and B is moving with respect to which will be having in a velocity with respect to when it is moving with an angular velocity. Now coming to this, so note both the tangential and radial velocities are denoted the same, so that the tags radial and tangentials has been added. Means we can able to produce the both the motions at a similar tag. So that is the reason which will been added, that is about the tangential and radial motion. So the sliding link will be having it. This the sliding will be link will be having two relative velocities. So the radial and then a tangential velocities. So that will be they are normal to each other, and the true velocity relative to A is vector. That is the vector of both the velocity. We can able to see this velocity, that is vector of a tangential and a vector of relative motion is the sum of both, that is as shown in this figure, both the vectors of a tangential and both the vectors of a radial. Coming to this, so the two vectors that is has been denoted by using the diagram C1 and C2. The velocity of link C is relative to point A, and that is a vector what we called as a C2. So you can able to see this C1 and C2 are the two vectors, that is for a tangential and a radial. So this is the velocity of a link which is relative to A. Where you can able to see this. This is relative to the velocity of a link A, which will be having a vectors, that is C1 and the C2 vectors. Coming to the crank and connecting rod and then a piston. So considering this mechanism, let's freeze the motion. That is, we want to freeze the one motion where you can able to see in this direction the velocity of the B which has been fixed, and the diagram is called what is called as a normally piston and connecting rod. But when coming to this, it is a space diagram based on this relative motion which is being developed or how it has been considered. We going to do this. Now coming to this diagram, where we can able to see the point A, which is having this is a connecting rod, this is a link 1, and this is a fixed link, where it going to convert from one motion to the other motion. So it is been, now if the piston starts moving in the forward direction, automatically this linear motion will be converted to this rotary motion. Again, when it is coming from the backward direction, again this linear motion will be converted to the anti-clockwise direction, that is about a rotary motion. So this is how we can able to convert the motions from one form to the another form with the help of this crank and connecting rod and the piston. Now, see here the piston, the above the frame is fixed, only the motion which will be the reciprocating motions will be takes place. Now considering the point A and the B, which is having a connecting rod with respect to O, the O to A is having a connected the link, and the theta is an angle of that particular link, and VA is nothing but a velocity of an acceleration at O, and VB is nothing but a velocity at a point A with respect to B, and VBC is nothing but a vectors at point C, because when it is moving in a linear motion, it can able to produce the radial and the C is can able to produce the radial and tangential velocity. So considering these motions, we can able to draw this diagram. We can able to see this. So vector at B and vector at A and vector at O. We can able to see this. O is where the link has been connected to A, and from A to B one more link, that is connecting rod, has been connected. So hence AOB. So OAB. So with respect to this velocity. So this is how we can able to identify, or how we can able to draw the space diagram with respect to this crank and connecting rod and the piston. Coming to that, so every point and every link has a velocity through the space. So first we label the first we going to identify the center of rotation. So often at this this is where the letter O, where we going to identify that the point O, and point A can only move in a tangential direction. Now when you want to fix the O, when you want to fix the O, the A can able to only can able to rotate in the tangential direction. So similarly, when we going to fix the that is a tangential direction, so the velocity of the A is the relative to the O, and also O is the absolute velocity to the vector is normal. So the crank and it is designated as a VAO, where you can able to see this VAO with respect to the tangential velocity. Now coming to the, suppose that we are having a point at A and everything else is moved with respect to relative to U, then looking towards the B, when coming towards the B, again it would appear the B is rotating relative to U. U is nothing but relative rotating towards your direction. That is a tangential velocity, that is VB is denoted as an A. So VB, how we can able to denote that A is nothing but which is moving in this particular direction, VB by A, automatically VB by A, which can able to be moves in this particular direction. So now coming, the direction is not, it is not always obvious, expect that it is a normal to the link. So considering the link of OC, so since both the points are fixed here, so hence the no velocity between the this VB and VA and VA, so there will be no velocity in this particular conditions. So this is how we can able to obtain the space diagram for a crank, connecting rod and the piston. So this is how we can able to even obtain for the slider crank mechanism also. Thank you.